Yeah, thank you. So yesterday, we learned about the basics of quantum error correction, the quantum circuit model, and in particular stabilizer error correcting codes. I just want to recap a little bit the final theory that we put down. So we usually have n physical qubits. And we write down n minus k operators, so-called stabilizers or stabilizer generators, that generate an abelian subgroup of the n-qubit Pauli group. Abelian meaning that these stabilizers Si all commute. So Si, Sj is 0 for all Si, Sj in this stabilizer group. And if we now take some state on this n-qubit Hilbert space, each Si we will enforce on the state to be the +1 eigenstate of each Si. And if we then count, we have n minus k of these n, then the Hilbert space, we drew this box yesterday for 3 qubits, where we had 8 states, which we labeled, for example, with 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 1, 1, and so on. Then if we have n minus chi stabilizers, yesterday we had Z1, Z2, and Z2, Z3 for the 3 qubit repetition code. Then each of these stabilizer generators will split the Hilbert space in half until we're left with a k-dimensional logical subspace. In the case of the 3 qubit repetition code, it was spanned by the basis states 0, 0, 0 and 1, 1, 1, which then, which is then our logical subspace. If we had some error, an error sent us to an orthogonal subspace and generated, if we measured these, if we measured the state, the so-called error syndrome, and I will. The syndrome was a vector of zeros and ones. There were n minus k of length n minus k. And if the now yesterday, for example, an x1 error sent us to an orthogonal subspace, and if we measured this first operator, we had a -1 eigen. We got a -1 outcome, and the second operator for x1 still got a +1 outcome of this syndrome vector. In general, we can also, for each of these, so in the syndrome vector, the ith entry is then either +1 or -1. Sometimes in the following, I will probably also use 0 and 1 instead of -1 and +1, because on our computer it's easier to work with zeros and ones. If the error that sits on the code space commutes with the ith stabilizer generator, or if the error anti-commutes with the ith stabilizer generator. Okay. Then in this logical subspace, we had the logical operators that perform non-trivial actions within this logical subspace and simulate the physical Pauli operators on physical qubits. These logical operators, or non-trivial logical Pauli operators, they were elements of the normalizer of the stabilizer group in P, and we quotient out the stabilizer, so all the elements that commute with stabilizer generators, but are not stabilizers themselves. So for some logical Pauli operator, it holds that this operator commutes with all the stabilizers. And if we choose a set to simulate the physical operators and label them by X and Z, then this pair anti-commutes. But if I put a J here, so if we have more than one logical qubit, so if K is larger than 1, then they will commute. Okay, this was the very basic theory that we ended up with from a group theoretic perspective. If you want, I was asked yesterday for a good reference, and I can recommend like the original reference. I think is pretty nice. It's Gottesman thesis. If you just type this into Google or into arXiv, you will find it from 1997. There, this is all laid out a little bit more in detail, a little bit more rigorous, but that's basically all we need to know for now. All right. Today, we will see how today, this day is called fault-tolerant universal quantum processing. I, again, don't know how far we will come, and we'll probably shift the rest of it to Thursday, because there's two important things we want to cover today. First is so-called topological toric and sophist codes. We ended yesterday after this repetition code, where we found that actually there's also single qubit set errors that are logical operators. We found that, for example, we need 5 qubits to correct for one arbitrary error at least, and we had this so-called Shaw code, which was a 913 code that could then correct for one error, because this is the minimum distance, the minimum weight of a logical operator, which then tells us how far we can go from our code set in order to still recover it. And topological codes, as you will see, are a nice new class of codes where you can get very good protection against errors. Then the second thing I want to cover is how to perform logic in error correcting codes. Because for now, we just know how to do logical Paulis. But we learned yesterday in this quantum circuit model, as you can still see here, we also want, for example, a Hadamard or a T-gate or a C0 between logical qubits so that we can perform universal quantum computation on this encoded qubits. Yeah, and then, if time permitting, we will talk a little bit about more advanced noise models and principle of fault-tolerant circuit and logical gate constructions. Again, if you have any questions, interrupt any time or use this poll board. I will keep this up for 1 second before we start. All right. Still see some phones up. I will also note in the corner pe.app/QECQ and A. Q and A. Okay. Topological codes. So yesterday we saw in the poll that lots of people here are physicists. So topology kind of maybe means something to you. And the idea of topological quantum error correction is that we will use robust global features that are invariant under local perturbations to encode quantum information. So what you can, for example, here see on the right is lots of qubits that are put on a torus. And what we will now develop is, or what I will now show you, is a code that encodes logical information on global invariants, like this red circle that you can see here, that red string. And we can protect against local perturbations, so small errors on single physical qubits. This code is called Kitaev's toric code because it was discovered by Kitaev in the early 2000s. I think even 1997, the first considerations in that direction were made. And in this code, we will put qubits on the edges of a lattice. So for now, you just think that this lattice goes into both directions all the way into infinity. And then we will define two kinds of stabilizer operators that commute. Namely, every plaquette, as you can see here, will be a 4-body Z stabilizer. And every vertex, like this here, will be a 4-body X stabilizer. And as you can see, every plaquette and every vertex, they always share 2 qubits. So if I place the next plaquette of Z stabilizers here, we can see that it overlaps with the neighboring X stabilizer on 2 qubits. And therefore, they anti-commute once, they anti-commute a second time, the X and the Z, and these operators commute. We then tile the full plane with these operators. We ensure that we have ensured that these terms commute, and this defines our code. As we have learned, we just need to write down a certain number of stabilizer generators, and this will be enough to define a code. We don't know yet how good it will be, but we'll come to that. These Z operators will then again detect bit flip errors because they anti-commute with the X operators that represent bit flips. And the X stabilizers will detect phase flip errors. Okay, now we can think of this also from a physical perspective. And write down a Hamiltonian for this model, as you can see here on the top right, where we just write down a Hamiltonian where the ground state are valid logical states. And as we have learned, valid logical states are +1 eigenstates of the stabilizer generators. So in order to have the lowest energy state, a logical state, we have to put a minus sign in front of each stabilizer generator, and then this H is just arbitrary value of with an arbitrary energy that doesn't really matter. But then, if all stabilizers are +1, then this the ground state will be a valid logical code state. How much information we can then encode depends on the degeneracy of this ground state, which is similar to we split this Hilbert space, or which is identical to we split this Hilbert space until we have k degrees of freedom left in which we can encode quantum information. And on such a, if we put this lattice now on some manifold like this torus, the ground state degeneracy depends on boundary conditions and of the topology of the surface. And we can now think of how many constraints are still left. So if we look at the torus with periodic boundary conditions, I will just try and draw torus here with periodic boundary conditions. So this wraps around in this direction, this wraps around in that direction. and then we count how many, then we have to count in order to find the ground state degeneracy, similar to we count how many constraints we still have open. We've placed the qubits on the edges. So if we have a dimensionality of n by n, how many qubits are there in total? N squared. Number of qubits. And someone said n squared, is this correct? If we place them on the edges, we have 2 times n squared, because we have like 1 times, like once n by n, and then we have this inner lattice as well, where we have n by n qubits. The number of plaquettes, so the number of plaquettes, however, that is n squared. And then we have to, it's n squared, and then every plaquette has 2 unique qubits, so that also gets us to this 2n squared. Then in order to find the number of constraints left, we have to find the number of independent x and z stabilizers. So one might think, okay, every plaquette has 1 x stabilizer, so that's n squared, and every or z, and every vertex has also 1 x stabilizer, so that will also be n squared. And if I now check how many constraints are left, this would be 2n squared minus n squared minus n squared, which is 0. So do we encode 0 logical qubits in this code, or am I missing something? Probably I'm missing something. We have periodic boundary conditions. So if I multiply 2 plaquettes, for example, this Z operator here, let me use a color. Z, 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 Z. And the neighboring one, I will make a bigger operator. And I can take the product in every direction of all of the plaquettes, and I will end up with identity. So this is one constraint that we lose. So the product of all Z operators on this lattice is identity. And the same holds for X. So the product of all X operators on the vertices is also identity, which gives us 2 constraints that we have still that we have open. So it's only n squared minus 1 independent X and n squared minus 1 independent Z stabilizers. So there's enough space in order to encode 2 logical qubits. Because now we have 2n squared minus n squared minus 1 minus n squared minus 1, which is 2. So ground state degeneracy of 2. Okay, what are these logical operators? And I've already hinted that there will be some notion of locality and some notion of global operators. And if you can, you can already see here, every stabilizer is a closed loop, either like just one plaquette, or if we multiplied it with another one, it gets bigger, and so on. And we can deform these loops all around. However, they always live on the surface of this. Like they start being local, but then they always live on the surface of this torus. The non-trivial operators are global operators that cannot be collapsed to these local ones. So they are string-like operators that wrap around the torus. So you can see here depicted on the top, if we wrap around the whole of the torus, we can never, by multiplying it with stabilizers, collapse it to a single stabilizer. In this picture here, where we imagine this going on and then wrapping around the torus left and right, these are the smallest weight logical operators are those that, for example, here, this x1 that wraps around here, and the corresponding anti-commuting partner is this z1 here, and they overlap on the single qubit here, which verifies they overlap on one qubit, so they anti-commute. We can then also check again that these operators commute with all the stabilizer generators. So for example, this x1, it will always pass these Z plaquettes. It will always enter one and then exit. Because it enters and exits, it will always, no matter how we multiply these stabilizers, so even if we do like a larger loop, it will always enter and exit, overlap twice, and therefore commute with any Z stabilizer. It trivially commutes with any X stabilizer. And the same, or vice versa, it holds for the Z strings. So such a Z logical operator, it will always have even overlap with X stabilizer generators and therefore commute with them. Oopsie. Okay, I've also already mentioned the minimum weight. So yeah, we can change the weight of those logical operators by multiplying stabilizers, but the minimum one are those that wrap around the torus very straight, in a very straight way. And on a d by d lattice, the minimum weight, on an L by L lattice, the minimum weight therefore is L. So we can write down the parameters for this toric code on a torus, and they are then 2L squared, 2, and L. Okay, what I want to already tease a little bit, maybe for tomorrow, is if we take L to infinity, then these parameters, yeah, n, k, and d, will scale as n, order 1, and order square root of n. This means that if we make this code larger and larger and larger, the rate, so the number of logical qubits that we encode per physical qubit, will go to 0. And the distance will scale with the square root of the number of physical qubits. What this means, we will talk about a little bit tomorrow, but you can already imagine that this requires quite a big amount of physical qubits in order to encode information, but the protection, I can promise you, is quite good. And this we will see today already. Okay, there's one way to get around this order 1 number of logical qubits, and maybe some of you who have some developed some intuition now can tell me if I have a pretzel like this, and I would define now a code on this topology. So I place this rectangle, the square lattice on there, and I do X stabilizers and Z stabilizers the way I've shown before. How many logical qubits I would encode on this pretzel? 6. Someone's saying 6. Why? Yeah. Yeah, that's a very good answer because it's the correct answer. Indeed, as before, around every hole we could wrap X and Z logical operators twice, so to encode 2 logical qubits, and the same will hold for each other hole. And then with each hole we can encode 2 logical qubits, 3 holes, 6 logical qubits. Now maybe you can already, maybe you can imagine that if we put more holes in there, the distance will shrink, and this is also, that's a trade-off, which if you're interested, there's a famous bound called the Bravi-Poulin-Terhal bound from 2009, 12, I think, I'm not sure, where they show that, yeah, there's a trade-off if we use Euclidean space. There's a trade-off between the number of logical qubits we encode, the number of physical qubits we have to use, and the distance we can get. Okay, now we will look at how errors are detected and how we can correct errors in this Toric code. So again, we will measure those stabilizers like in the repetition code in order to detect errors. And then from these syndromes, yesterday we wrote down a lookup table. So we had these different syndromes here. For different errors, x1, x2, x3, we had different syndrome vectors and then could map it in a lookup table back to the correction that we want to apply. Similar thing we will do for the Toric code. We will measure the stabilizer generators, and again, if an operator like the Z operator that we measure anti-commutes with the error, then we will get a -1 measurement outcome, and which then signifies the occurrence of an error. Now here, we can also think in this Toric code as errors as gap excitations of this Hamiltonian. So every error will have a -1, or will have 2 -1 outcomes for adjacent stabilizer generators. And if you remember the Hamiltonian, there was a minus sign, so the energy will be a little bit higher. Now, if you look at this, we will now only consider bit flip errors. So we can forget this upper left part. And I will show you a few pictures, and I want you to tell me where the error might have happened. These are 2, 3 small exercises. And then after that, we will generalize this to arbitrary errors that can happen on there, and then we will play a little game. Okay, first, where's the error here? What has probably happened? Where has probably been the bit flip error? Was it here? Who's for here? No one? I've already shown this before. So the error that has probably happened is always next to, yeah, every error will always flip the adjacent syndrome bits, and therefore it will probably be here in the middle. Now we will be correct. We will be successful if the correction plus the error has no action on the code space. So in this case, we found the correct error, and we will annihilate it, and we will be in the same logical state. Okay, I have a second example. Now we see this. What error could have triggered this syndrome? I see someone like drawing a loop, something. Yeah, let's go, for example, if I put an error here and here, this will indeed produce that syndrome because this plaquette here, this has even overlap with this error, and only the endpoints of such a string here will violate the adjacent syndromes. Is this the only option? Symmetrical to them? Yes. One sec. I could have also had an X error on these 2 qubits, and this would produce the same syndrome. Is this a problem? You're saying yes. Why? Okay. I told you we only need to make sure that the code space, that we don't do non-trivial action in the code space. Okay, let's assume that I do this correction, but this has actually been the other error. Does this change anything in the code space? This X operator? It's a loop, exactly. It's a loop, and such a loop is, in that case, an X stabilizer. So this operator, so instead of correcting the real error, we just corrected it towards another stabilizer, and we know that the stabilizers on the code space are +1 eigensets, so they do not change anything. So this was in fact not a problem that we made this other error. So if the correction plus the error is in the stabilizer group, then we're also fine. The last example, and now I want you to imagine that we wrap around in this direction. What has probably happened in that case? Now there's again two options. It could be a string like this, or it could be a string wrapping around. But now, is there a problem here in this case? I see some heads nodding. Indeed, this was one of the non-trivial loops that wrap around the torus. So in that case, we would have a problem and indeed made a logical error. So if the correction plus the error is a logical operator, then correction fails. Okay. We will now first go from a torus, because it's complicated, because you have to think around the boundaries, to something which lives on a plane, and go from the toric to the surface code. And for that, we again need to make sure that all of these conditions for the logical operators and for the stabilizer generators can be fulfilled, and that we still have enough constraints left in order to encode logical qubits. This can be done by cutting boundaries in this torus, namely a so-called smooth boundary on this side and a rough boundary on the other side, which I also indicate by this. It's almost like a carpet, which has like a smooth side and those rough strings on two other sides. And this ensures that if we now put 3-body X stabilizers only on the rough and 3-body Z stabilizers on the smooth boundary, then we can still encode one logical qubit. So in that case, we lose those logical operators that have been on this second lattice. So there has always been, if you remember, in the toric code, there have been always one X operator that lives on one of the two sublattices and one Z operator on the other sublattice. We lose one of those. Because such an X operator would not commute with the boundary stabilizers. So we lose those. However, this Z operator here trivially commutes because Z and Z commutes. Okay, so we now are on the surface. We have lost one operator, but we can still do the same counting as before, and we will find that for this code, for the surface code, we will now have on an L by L lattice, we will have how many physical qubits? L squared, 2L squared, almost. I have L squared on this outer lattice, but then I still have this inner lattice, but this now only has exactly L minus 1 squared. Then I already told you we encode one logical qubit. And the distance, so what's the minimum weight of such a logical operator, X or Z? It will again be L, the linear dimension of the lattice. Okay. Next, now that we have the surface, I want to talk about decoding with more than just one or two errors that we had. here. And for that, yeah, we again look at bit flips only. We have this surface code here. So again, bit flips can now happen on each of the edges of this lattice where qubits sit. And I indicate, because we don't know where the bit flips actually sit, we just know the plus or minus 1 outcomes of the stabilizer measurements. And I indicate with these green circles where the syndrome measurements have actually been -1. Okay, we've seen before that the errors are always string-like operators with excitations at the end. So before we had one example where we had an X error like this, and then we had these syndrome excitations on the side. Now I've drawn some arbitrary error configuration. Can someone tell me how I could, for example, decode this? So if we take this example up there and we add one error, oops, then we will always have the error on the endpoints of the syndromes on the endpoints of this error. So we could, for example, just, I don't know, assume that there has been some error here like this and some error here on these edges like this. Because if we then place these bit flips here, this error will have the same syndrome as the syndrome we have measured, and the correction that we applied will be will put us back to the code space. So there will be no more syndrome left. Okay, this is not just looking at this and doing it is not necessarily the best strategy. And I put as title for the site near optimal decoding of the surface code. Now, when we think of how we decode, we always have to assume some kind of error model and some kind of strategy. So if I assume bit flips, and I for now also assume that on each single qubit we will have this bit flip channel, that with 1 minus p, nothing happens, and with p we have a bit flip. Then the most probable error, or like let's call it a most likely error decoder, so the most likely error that can happen will be the error that has the lowest weight, right? Because as long as p is smaller than 0.5, it's always most probable that an error with the lowest weight has happened. We can find this lowest error with a strategy that's called minimum weight perfect matching, and I will now introduce this strategy. And for that, we take the syndrome graph, and we will build a matching graph from that. A matching graph does what I did before by hand. I just try to find some string that matches these syndromes, because then I can draw these string-like errors that will annihilate these excitations. But now I will put connections between every single of these excitations. And what I also put is boundary nodes, because on this surface code, we can also connect to the boundary. So maybe I show an example on the actual surface code here. So here, if we had bit flips, then a bit flip in the bulk here will always give -1 for the 2 adjacent Z stabilizers. However, if we're close enough to the boundary, for example down here, an X error at the boundary, for example here, will only flip 1 stabilizer, namely this one here. So we can actually also draw a string from the boundary to the inside that will not violate a pair of stabilizers, but just a single one. And in order to account for that, we also introduce these two boundary nodes. So yeah, these two boundary nodes. We will then weigh these edges according to the distance between these excitations. So for example, yeah, and we will use the Hamming distance because we're here on this square lattice where every edge that we take, we just count as one. So for example, between this excitation and this excitation, we would put 4 errors as the shortest path between these two excitations. So we give this this edge a weight of 4, or yeah, you can also do the other way around and then do some other algorithms. But for now, we just weight it with the Hamming weight of with the Hamming distance between those two syndrome excitations. Another example, this lower excitation to the boundary gets a Hamming weight of 2. And we do this for every edge. Okay, now we did this for every edge. And now we have to find a minimum weight perfect matching. So we have to match all of the excitations with the minimum weight, because that gives us then later a solution with the highest probability. And in this case, so there's algorithms for that. Most famously, the Blossom algorithm, which does this in n cubed, I think, or n squared, at least polynomially. Yeah, if we apply this algorithm, we will find that the lowest weight matching actually matches these two and these two syndromes. Any other matching, for example, we could also match these two, and these two, but they have a weight of 8, which is larger than 6. So we would need a total of 8 errors in order to annihilate these excitations, whereas the minimum solution only needs 6 errors and therefore is more likely under our error model. For this, there exists also many libraries that do this in reality. Most famously is probably pi matching by Oscar Higgert, who's now at Google. And Google also uses this and variants thereof. And from this, we can then get the correction that we would apply in order to put us back to the code space. Okay. Now we know how to decode, but we still don't know how good we can decode. We know that if the distance is d, we can correct for d minus 1/2 errors. But yeah, how good can we decode? And for that, I also want to do a small live coding session, or at least a small Python notebook pressing run session. Let's try. Okay. I hope, let's see. I will do something else. Okay. Okay, is this approximately readable for everyone? Perfect. Okay. So I do this because this is approximately what my workflow in my real work looks like. Other than in yesterday's tutorial, I used some libraries. In particular, I use one called pi matching, which does the decoding for me, so I don't have to care about that. And I use one that's called STIM, where I can build quantum circuits. And I already have some, there's already some method that generates some quantum circuits for me that read out the syndromes repetitively. So I will show you, for example, a distance 3 circuit that reads out those syndromes. This is not too important, but here you can see the circuit diagram. So this is the circuit that reads out the syndromes. For example, we can follow, it looks a little complicated, but it's just because it's compactified. But we can, for example, follow this, this one bit here. It initializes in 0, that's what this R means. And then it does a controlled X to this qubit. Then it does a controlled X to this qubit. And then it reads it out. So it performs a Z, it performs a Z, wait, let me see whether it, oh, wrong qubit. Let's look at this one up here, which is easier. So this upper qubit to 0, we initialize in plus. Let's draw it here. Then, so we initialize in 0, we perform a Hadamard to put it to plus, and then we couple it to 2 qubits. And then we again perform a Hadamard and read out in 0, which is the same as an X measurement. So this is an X measurement similar to the one that we've seen in the repetition code. And this reads out one of those boundary stabilizers of a surface code. Okay, so this is the circuit. And now, this doesn't, and now we will put some noise in the same way that we've put before. So here, I now put 1 round of noise just before I measure those stabilizers. And what I will now do is I will sample this circuit in the following way. I just sample different errors from the circuit. So each of those now is a depolarizing channel. And after that, I read out the stabilizers and I get the stabilizer measurement outcomes. And from those stabilizer measurement outcomes, for example, here I have some X stabilizer measurements that give me now 0 or 1, depending on whether there's been an error or not. Now these are those syndrome vectors. There's 10 of them because I sampled 10 times, but you see, because it's a probabilistic, there's probabilistic errors, each run at different measurement outcomes. Now I can take these and feed it to the decoder in the same way as before. It's a quick reminder, there's some error, so we sample the actual error. We can do this on the computer. We would not be able to do this on the quantum computer. We get those syndromes. We get the syndrome or matching graph. And then we feed this to the decoder that gives us a minimum weight perfect matching, which we then apply as a correction. This can actually be done very easily. Here. So I can just call in this library decode. This is all you see here is just I now sample different sizes of, here I sample different sizes of surface codes, and then I sample different noise strengths. Then I get the circuit, I build this matching graph, then I sample the circuit, get the syndromes, the rest is not so important, and decode. After each shot, so let me scroll up again. After each decoding, so when I have this correction, I can check on my computer and I can compare the correction to the actual error that has happened. And I can check whether whether the correction plus the error is a logical operator, or whether the correction plus the error is a stabilizer or even identity. And when I do this, I will actually run this because it's actually pretty fast. So I sample for each distance of a surface code and each noise rate, I sample 100,000 shots, and you saw it just took 5 seconds because it's all very well programmed, and I get the following curve. So here, this we have already seen yesterday in the repetition code. Here I sample physical error rates, and here is the probability of a failure. So whenever the correction plus the error has been a logical operator and not a stabilizer, I just count +1 on a counter, and then in the end, I calculate a logical error rate. And you can see here, what I have promised you before is that, and what I've also talked about yesterday, is that if we have a code with distance d, we can correct d minus 1/2 errors, and then the logical error rate starts to scales for low physical error rates as p to the d minus 1/2 plus 1, because that's the first weight of error we cannot correct, which is for distance of 3, 5, 7, would be a quadratic, a cubic, and a quartic scaling. And you can see here in this log-log plot that this is indeed the case. Distance 3 scales quadratic, distance 5 will scale cubic, distance 7 quartic, and so on. Now this also gives us a threshold, so a point where if we make the system larger and larger, below this point we will always correct, and above this point we will always be wrong. And this is the threshold, which you can see up here. And oops, if we look at this in a linear plot, you can also see this value. And this value for this noise model is approximately at 13 point something %. So we can actually asymptotically allow for a bit flip, or in this case, a depolarizing error rate of up to 13%, and below that we can correct for any, we'll always correct. Okay. Perfect. Now, this as a small hint for tomorrow, or maybe later today even, depending on the time, we this 13%, or if we just have bit flips, it's 11%, this threshold. This is only for this noise model where we place the noise just before the measurement and nothing else is noisy. If we allow for more noise anywhere else, this will go down to approximately 1%, this threshold. I can already show you quickly if we do a circuit level noise. One sec. Here. All right, so everything that is now red is noise, so there's much more noise in the circuit than before, but we can still do the same and run. Now it takes much more time as well because there's more noise and we have to do more work to decode. Details about this later or tomorrow, but just as a quick teaser, do you think the threshold will go up or down if we allow for more noise? it will go down. You've maybe already seen. It will go down to this approximately 1%. So now we're way below, or we're a little below this 10 to the minus 2, but we still get a similar scaling. Yeah, I didn't put error bar, so this doesn't look good, but there's probably an error bar that will put this to the correct scaling. All right. Now, I want to try something because these thresholds are also always decoder dependent. And this decoder that we use now is a machine, but I've also shown you that you can do it by hand. And now you have the task, I want to find the threshold of this room decoder. So if you scan this, this code, or if you type in this website, you can do it with your phone, or you can do it on your laptop. You will go to a website. I hope it doesn't crash with the amount of people. I'm not a web developer or anything, and I had a lot of help by a certain large language model in creating this website. But you can decode yourself. And it would be great if we could do approximately, at least for the first 1 or 2 tries, distance 3, distance 5, and distance 7. So we can maybe even get a threshold. I will put this back in a sec if you're not there yet. I will now just quickly show you how you can use this. So here on the left, you can just choose your distance of the surface code, then you can start the game, and then you will always get a syndrome like this, and then you have to guess what the error is. So if you click somewhere, you will apply the correction immediately, and you will see whether you went in the right direction or not. So in that case now, I did not annihilate the syndrome because we learned that, yeah, I should probably decode here, and then everything was fine. Yeah, and then you will get a certain selection of errors with increasing probability, and in the background, yeah, I calculate these logical error rate curves. And now I give you a few minutes to play around a little bit. You can also then, after you did 3, 5, 7, try some other distances. And then in a few minutes, we will see whether we can find the threshold of this room decoder. I think you can play on restart. Put on restart. Is it working? Okay, so a few more distance 7, please. Yeah. You can also look at it. It's like on show stats on the. Okay, I'm waiting for a little bit more statistics. I will also play here. Making a lot of logical errors. Okay, let's do 2 more minutes. I do a little bit of distance 5. Okay, you can continue to play all day, all night if you want, unless but not for the next 25 minutes. Yeah, for now, if we look at the stats, we can, I think, already see. I will clean it up a little bit and show you a nice curve maybe on Thursday. Yeah, but I think we can already see that the distance 3 is kind of like the worst within error bars. And for example, here, distance 6 or distance 7, yeah, they lie below, as we would expect from a good decoder that performs as we expect, that it can correct the right number of errors. Okay, but yeah, as you can see, it's not so easy to find the minimum weight solution, especially if you don't try. Okay. All right. Yeah, I have about 25 minutes left. Perfect. Yeah, then I just want to yeah, quickly advertise some experiment where people in our group have actually been involved from the theory side, particular Markus Müller, where they implemented a surface code in the lab. They used a so-called Surface 17 code. Now, this is a code that is slightly different than the code that I've shown before. Before we put the qubits on the edges of a lattice. So the smallest distance 3 version of this surface code would have 9 plus 4, so 13 qubits, encoding one logical qubit with a distance of 3. However, this, if you now want to implement this in the lab, and you want to read out the stabilizer generators with ancilla, you would need for each stabilizer, for example, in the superconducting architecture, one additional qubit, so that you would end up with a total number of 25 qubits. However, there's a slightly more compact version of these surface codes, namely by cutting some qubits at the edges and rotating it to get this rotated surface code, where you, instead of having weight 3 boundary stabilizers, you now have weight 2 boundary stabilizers. But you can check again that every stabilizer commutes, and that you also have these logical operators. And now you can also think of this as putting the qubits on the vertices. This was a little bit too much. On the vertices of a square lattice, and then you get a code that has only 9, 1, 3, 9 physical qubits only, and you would need 8 additional ancillary qubits, and that's how you get to the Surface 17 code. They built this chip in the lab using superconducting circuits. In particular, Nathan Lacroix and Sebastian Krinner. Nathan is also now at Google, I think. In the group of Andreas Wallraff at ETH Zurich. And they implemented the first repeated QEC cycles in surface codes using this, this chip. Now, they were the first, but the best for now come from the US. So just last year, Google put out a paper on quantum error correction below the surface code threshold. So I've shown you this 1% value, where below, if we increase the distance, we will get better protection. And they have shown for the first time in a chip that if they use quantum error correction, so now here you can now see the logical error probability, and here you can see the number of error correction rounds that they perform. And they have seen that if they go from distance 3 to distance 5 to distance 7, they will actually increase the protection over time for their logical qubit. This was the first time that this has been shown, and they have also shown that with error correction, they can actually perform better than the best physical qubit. So this line here, this green line, is the best physical qubit of this chip. And if they encode a distance 7 surface code on their chip, they can actually keep this logical qubit longer alive for longer than they could the best physical qubit on this chip. Okay. Now the last 20 minutes, I want to start talking about logical gates and stabilizer codes. For now, we have just, as I mentioned before, we look, question. Yes. Yeah. Yeah, I will talk about like circuit level noise models tomorrow, because the last 20 minutes, tomorrow on Thursday, because the last 20 minutes are not enough. But yeah, basically, if we have a circuit that implements this the stabilizer measurements, and at the very end there's an error, we cannot detect it unless we do another round of error correction in the next in the future, or at the very end we will, for example, measure out the single qubits in the Z basis. And then this will collapse to a valid logical state or not. But we can reconstruct all Z stabilizers from these Z measurements, and then we can use this to correct the bit flips that happen almost at the very end. Okay, yeah, we have talked about stabilizer measurements. And these stabilizers, what they do on the code space is basically nothing, right? They remove, with the correction, they remove errors, but they actually implement something like the identity on our logical state. We have seen the logical X and logical Z operators, which implement the Pauli group. And now we also want to perform universal quantum computation. And for that, we need Clifford gates like Hadamard and C0, and a non-Clifford gate like the T gate. So we also want these gates, these physical gates, to be simulated on the logical level. I will focus for now on the Hadamard gate. So the Hadamard gate on the physical level, if you conjugate, yeah, we know that the Hadamard gate on a 0 state transforms it to the superposition 0 plus 1. But in the stabilizer formalism, we don't want to look too much at the cats. We want to look at the operators. So what the Hadamard does, it transforms a state that is stabilized by a Z operator to a state that is stabilized by an X operator. And this we can express by calculating HZH as X or HXH. Yeah, we could put a dagger here, but it's self-adjoint, so we don't have to. Or H at X is Z. An encoded Hadamard operator should do the same with the logical operators. And we should also verify that yeah, this holds for the logical Y operator as well. And it should be self-adjoint, so yeah, it should also keep the stabilizer group invariant so that we stay in our code. So these three conditions, or yeah, two conditions should be fulfilled. We should have the correct logical actions of our operators, and we should keep the stabilizer group invariant. Now, we have seen that in our surface code, for example, we can implement the logical Pauli operators by just applying physical X operators, single qubit X operators on physical qubits. So one might think, okay, yeah, well, maybe I can just do the same with a Hadamard. Let's try that. We take our surface code and we apply single qubit Hadamards on each of the qubits and see what happens. Now, the Z operator, yeah, let's look at the stabilizers first. We know that H transforms Z to X and vice versa. So each of those X plaquettes gets transformed into a Z plaquette, and each of those X vertices gets transformed into Z vertices gets transformed into an X vertex. And the same for the logical operators. Such a Z operator gets transformed into an X operator, but in the wrong direction, horizontally instead of vertically, and vice versa. So these conditions are not fulfilled. This condition plus, in particular, the condition that the stabilizer group is invariant is not fulfilled. Obviously, because X stabilizers get mapped to Z stabilizers, but on different qubits. So we cannot trivially just apply Hadamards on each qubit to perform this logical Hadamard. So we have to do something more. Yeah, and I want to use the last 15 minutes now to show one way how one can, in general, implement logical gates, in particular the Hadamard gate, and then maybe show one trick how to get around that in the surface code. But yeah, we will start by reminding you of something which you may have already seen, which is state teleportation. So this circuit here implements a state teleportation, which we can verify. So we have a physical state psi, and we couple it to an ancillary qubit. We measure out the state in X, yeah, apply Z correction, and have teleported the state. We can verify this by just calculating. So I will do the calculation. We start with psi O times 0, which we can, in most generality, expand to alpha 0, 0 plus beta 1, 0. The first C0 we'll put this into alpha 0, 0 plus beta 1, 1, which is also equivalent because 0 is 1 over square root of plus, plus, minus, and 1 is the same with the minus sign. So this is the same state as having alpha and then plus, 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 minus, plus, minus, plus, plus, minus, minus, plus beta with minus signs in front of those terms that only have one minus term. Okay, I do this because I now measure the first qubit in the X spaces. So I only keep those states where we, so I keep the states where we have a plus if the measurement outcome is +1, and I keep the states where we have a minus where the measurement outcome is -1. So we can check what states come out of there. So if the measurement outcome is +1, or if the measurement outcome is -1, then we can do the calculation, and I'm sure you believe me that we'll get on the second qubit in a +1 outcome, we'll get alpha 0 plus beta 1. This is because we get plus, plus, minus for alpha, and we get plus, minus, minus for beta. And in the -1 outcome, we'll get alpha 0 minus beta 1. So in order to recover the initial state that we started with, we'll have to fix this phase, which is done by this Z correction. So what is meant with this double line is that if this measurement outcome X is -1, we do classical feed forward in order to do the Z correction, which then flips back the sign, and we end up with psi on the lower qubit. Okay, we can now use the state teleportation to construct a gate teleportation or gate injection circuit. And we will do this in the following way. We start on the lower left, and now we just do basic circuit transformations. My goal is that I want to implement a Hadamard on my state. So I want that in the end, I have Hadamard on my physical state, which I can do by just doing a Hadamard gate at the end after the teleportation. Now I pull this Hadamard through the circuit to the beginning. First, I pull it through the Z, and as we've learned here, if I conjugate, if I have a z for a Hadamard, I can also multiply again from the left with a Hadamard and get z Hadamard as Hadamard x, which is exactly what you can see here. I can play this game further and push the Hadamard further through. Then there is a rule that tells me that if I have a controlled x with two Hadamards, then here I basically have h, x, h, which is z. So what I basically did here is I inserted two Hadamards, which are identity on left of it, and then converted this to a z. And then finally, I will consume this Hadamard in my initial state so that I have this plus state here. And now I end up with a circuit where I don't have to perform this Hadamard gate anymore, but I start with a plus state, I do some state teleportation, but during the state with this correction, I will have performed the Hadamard on my quantum state. And now the funny thing is that I can replace everything in the circuit with logical states and logical gates. So this was all physical, but now I just, in order to signify the logical states, I put a bar on top of it, and in order to signify logical gates, I do the same, or for the C0 and the CZ, I just do this bar, but I can do the same with logical states. So instead of having to perform this logical Hadamard in some gateway, I can also prepare a logical plus state. Yesterday we have seen an encoding circuit, so I could also do this for the surface code, for example. And then instead of performing this logical Hadamard gate, I will just have to prepare this logical plus state. Yeah, and also I will have to perform this logical ZZ gate. But I will not have to perform this Hadamard gate again. Okay, I will quickly, first, are there any questions about this? This is conceptually maybe difficult, but I would recommend, in the same way as I have calculated here, you can do the same calculation for this circuit to convince yourself that indeed, without actually applying a Hadamard gate, you will apply a Hadamard gate on your arbitrary state. So you can do the same calculation, and you will end up with your final state will be when you start with alpha 0 plus beta 1. Your final state will be alpha plus beta minus. So you have effectively performed the Hadamard. Yes? Good question. It's a single qubit measurement. So if I have now this encoded, what I need to perform is a single qubit X measurement. And then from this X measurement, so basically instead of doing, these are then just single qubit teleportation circuits, but this will teleport the full entangled state. But from these X measurements, I can then infer eigenvalues of X stabilizers to also do error correction in that step. And I can infer the value of the logical operator, which will then determine whether I do this logical X correction or not. Okay, so we have almost all the ingredients to perform universal quantum computation, because I can do the same thing if I replace this Hadamard with a T-gate. So I could also do the same thing with a T. the only thing that changes is all these these were wrong, but I will show you maybe tomorrow the exact circuit. Some of the circuit transformation will be different, but I can do the same thing with a T-gate. And then what we still need is how can we entangle logical qubits. And this I will talk about tomorrow. In addition to Thursday. I just want to, as a very final last thing, show you a small little trick on how we can do the Hadamard in the surface code without this complicated teleportation circuit. Namely, something called the fold transversal Hadamard. Because maybe some of you see some symmetry here. So is there a symmetry between this code and this code? Transpose is good. It's basically transposed. We could also call it a mirror symmetry along this diagonal. So if I take this diagonal and swap everything around the diagonal, then I will get back to this code, but only for the stabilizers. Like what? Like this? I think it's the same. So if I swap along this diagonal, the blue plaquettes will go on the position of the red plaquettes again, and of the red stars, of the red vertices, and vice versa. And I will preserve the code space. So if I apply this Hadamard and then I do swap along the diagonal, I will actually perform a logical Hadamard on the surface code. However, I will have to swap these qubits, these qubits, these qubits, and so on. So this is also a challenging task. Okay, how we, tomorrow, as I said, I will talk a little bit more about entangling logical qubits. Wait, one sec. Here, entangling logical qubits. Then I will talk about this T-gate a little bit that I've teased right now, so how we can really get to universal fault-tolerant quantum computation. And I will finish with some aspects of fault-tolerant circuit constructions and some more modern approaches that we use in our daily research. And with that, I think it's enough for now. And if you have any more questions, please go ahead.